Right, I'll take that as a signal once you go ahead and get started.
Okay.
My name is Paul Berger. I work for the National Park Service. My current job is the regional hydrologist for the Alaska region. So I'm down here doing some volunteer work and soaking up some sunshine, because this time of year we don't get very much of that up there. As way of background, I have been doing geology and hydrology research here in the Guadalupe Mountains for more than 25 years. I did spend 11 years as the park hydrologist here at Carlsbad from '99 till 2010. So I've spent a lot of time above and underground here in this park and up in the forest. And I've worked with a lot of the different geology researchers that have come through and done a lot of the good original work here in the park. As a warning, I do have a tendency to speak geek. So if I throw out a term that you're just like, okay, I have no idea what he's talking about, you feel free to just like raise your hand and say, what the heck are you talking about? Or you can wait to the end and I can explain it at the end. But I'll do my best not to, but that's sort of my default language is total nerd, so forgive me. Hopefully you can at least get most of the stuff out of context. So what I'm gonna just cover is just some basic geography and geology of this whole area. Talk a bit about the reef development itself, what made the rocks that are under our feet. Talk about the changing hydrology, and hydrology is just the fancy word for water moving through the rock. And then talk about what most of the people here are probably interested in, which is the kind of the history of cave development here in the Guadalupe Mountains, and then cover just some of the cool little fun details. And then hopefully I've left plenty of time for questions, because there's only so much you can cover in this, and you never know who's going to want a lot more detail on a specific subject. But at the end, there'll definitely be opportunities for you guys to ask questions, and I'll do my best to either answer your question or point you in the direction where the answer is. So, as a way of geography, this is 260 million years ago, where we're sitting here. This is the paleogeographical map of basically North America, and there's the big UR here arrow. Zooming in, you can see this area is the Permian Basin itself is actually divided into two sub-basins. The Midland Basin, which is obviously centered around Midland, Texas, and the Delaware Basin, which is basically the part of the basin that we're in here. So you can see it's like, the Midland Basin's a little shallower, Delaware Basin's a little bit deeper. And all along the edge of that basin, we were basically in tropical conditions, so we had active reef growing. The earliest reef was the goat seep reef, and again, it was along that whole kind of U-shaped bend. The reef just grew right at the edge of that, of the edge of the deeper water. The reef organisms can only grow in fairly shallow water, because they still need sunlight for all of the processes to go on. So out in front of the reef, which is to your right, you had all of the material falling off the front of the reef. We call that the forereef for obvious reasons. Everything on the landward side, we call that the back reef. So you're really looking consistently at three different environments: back reef, the reef itself, and then the forereef. So the back reef for the goat seep was the Queen Formation, and the forereef was the Sherry Canyon Formation. And then as the basin continued to evolve, at one point sea level dropped, and you ended up with this big, basically fan of sand that came across all the old reef deposits. The reef building itself was pushed out into the deeper water, and you've got this very distinct bed, which we call the Shattuck Sandstone, that kind of marks the boundary between kind of the goat seep reef era of the whole system and then the Capitan reef. So this is representing how the Capitan reef grew on top of the goat seep, still right along that basin margin, big U-shaped reef. In this case, the forereef was the Bell Canyon, and again, that's just sediment coming across the lagoons, getting dumped out into the deeper water. Early on in Capitan time, because the sea level was rising so rapidly, the reef just kept growing up higher and higher, so the front was very, very steep. So what you had is a lot of big chunks of rubble, the reef rock itself kind of tumbling down into the deeper water. And that big jumble of rocks is called the breccia member of the Capitan. So in that early days, that's what it was forming. And in the back reef of the early Capitan time, you had the Seven Rivers formation, and that's just the lagoon deposits, behind the main reef. It's still primarily carbonate rock. So you have what's now primarily like dolomites. You see things on maps shown as siltstones, but the siltstone itself is still mostly carbonate. So it's not like a silica sand like you would think when you hear the term siltstone or sandstone. It's just part of the old nomenclature for the stratigraphy around here. And then in later time, as the basin really was stabilized, the water table the sea level wasn't rising super fast then. What you were having is the reef started growing out into the water, out into the water in front, and you end up with these shallower deposits, which are represented by the Yates, and then on top of the Yates is the Tansel. And to kind of orient yourself, the entrance of Carlsbad Cavern itself is up in the Tansel Formation, and then it gets down into the Yates, and the contact between the two is right at Devil's Spring. So just as you're walking through the cave, or if you're recalling your recent tour down into the cave, that's kind of where you hit that contact. And then when you get all the way down to Devil's Den along the main corridor, that's where you transition from the Yates Formation into the Capitan itself. In Carlsbad Cavern itself, we do not see the Seven Rivers Formation at all. That's a little bit further back because we're kind of perched more on the front part of the reef. So, as I was talking about, and you don't need to completely understand all those cool squiggly lines and stuff. This is a very nerdy picture. The most important thing are these vertical features that you're seeing there. These are syndepositional faults, and all syndepositional means is these faults were forming while the reef was still building up. And you had this big, like I talked about, the reef just was building very, very quickly upwards. So you had this very steep front, so big, massive blocks of the limestone itself were actually falling down into the deeper water, and then more reef rock would grow on top of that. And the reason that these syndepositional faults are so important is the whole reef rock itself was cemented together very, very early. Like almost as it grew, it filled up all of the pore space in between. So you're looking at a solid, impermeable chunk of rock. Well, you need to have some of these fractures in this rock to get water to move through it. And as I'll explain later, you need water moving through the rock to form these cool caves. If it was just solid chunk of limestone, we wouldn't really get any pockets. We wouldn't have these awesome caves. We just have a big chunk of limestone that I'm sure people who like to run quarries would really, really like. But because of these syndepositional faults, we have something much cooler than a quarry, which is a bunch of really cool caves. So, pretty much once the Permian Basin kind of no longer had any water in it, over time the water evaporated, it got cut off from the main part of the ocean. It was buried in several hundred or thousand feet of sediments on top of it, and then things in this area were kind of pretty chill until about 88 million years ago. And that was the start of the Laramide orogeny. Anyone who's familiar with the western US would know this is what formed the ancestral Rocky Mountains. It was a very long period of tectonics, and that's when this whole area started getting slowly uplifted again. Part of that uplift included a feature called the Alvarado monocline. And a monocline just means the rock did one of these, it's just coming along and it makes a bend and kind of drops down, as one block kind of goes up, half of it just ends up, the other half is down. And it's called a monocline because there's only one limb that is of it. So it's different than a syncline, which is kind of a U-shaped feature, or an anticline, which is kind of an A-shaped feature. The thing that was important about that is that actually that uplift created magma pulses of carbon dioxide. And that carbon dioxide was rising up through the system mixed with the briny aquifer water. So this is still like well below the water table. It's about 500 meters below the water table at that time. And the conditions were just right at that roughly 500 meter level for the CO2 rising up again through these fractures and faults in the limestone to form these very cool pockets of massive calcite crystals. So the initial phase, the pockets would form, and then when the pressure and temperature changed, you ended up with these huge pieces of dogtooth spar, or calcite crystals, which is what Dave here is looking at. Those aren't like stalactites, stalagmites, those are actually really big calcite crystals. So that formed kind of at that level throughout, but primarily the Capitan limestone itself, because that had the right conditions for it. But that was like, it's important because that sort of gives us a baseline of when, a bracket of when the caves could have started becoming developed. This is well below the water table. This has nothing to do with sulfuric acid. This is just carbon dioxide. So we have, starting at about 35 million years ago, we had the start of the Basin and Range tectonics, and that's what forms all of the big ridges and valleys throughout the west, starting in New Mexico all the way through Arizona, Utah, where you just have the series of big mountains and deep valleys in between. We're on the very far east edge of that. So what we had is the rocks started tilting up, and what that did is it actually created a catchment area. So now you have a high ground that can catch rainfall and can start moving fresh water down into those deeper rocks to where the limestone is. So you had this meteoric water, which is just the nerdy name for rainwater, and you've got the water and then microbes that are just carried with the water down into the deep aquifer. At the same time, in the places where the water is coming back up to meet the groundwater table, the water is taking advantage of those vertical faults and fractures to move up to the water table. And because of the chemistry conditions, you've got fresh water in a limestone. You're starting to enlarge some of those fractures and faults in the Capitan. Again, you're continuing to make good plumbing system for later cave development. There's some speculation that there were actually artesian springs in the Guadalupes. Currently, the only real artesian spring in the area is the Carlsbad Spring, there on the north side of town, sort of where the Pecos River suddenly reemerges and has water in it. That's where the aquifer comes out now. But there's some speculation that even like the entrance of Carlsbad may at one time have been part of an artesian spring system, that water would actually be coming up out of the entrance that we know of today, or some of the other entrances. Unfortunately, a lot of the evidence for that has been eroded away over time, so we don't actually see like really cool, tufa deposits from a spring or anything like that. So, in addition to the Basin and Range, we actually started rifting along the Rio Grande Rift, and this is a major fault system. Basically, the North American continent tried to split itself in half, starting about 25 million years ago. And this rift runs all the way from Mexico up through the Rio Grande Valley north, and it goes up into central Colorado. It's a failed rift because it didn't continue to break the continent apart. We don't have a big ocean there. But what that did is it actually continued creating this hydrologic system that it moved even more water and more microbes in. And during that time, what you had is now with all the fresh water, with all the bugs going into these back reef deposits, you actually started getting hydrogen sulfide being generated by microbes breaking down the hydrocarbons. And the Artesia group is just the Tansel, Yates, and Seven Rivers. That's just the geologic term for that whole package of rocks. It's one of the major oil producing zones in the early days of oil and gas development here in the Guadalupe Mountains. Completely different from most of what's going on in the Permian Basin now. They're looking at much, much deeper rock now. But you had this source of hydrogen sulfide coming out of those back reef beds. You also had some hydrogen sulfide being generated at the contact between those four reef beds and the Castile. And the Castile is a big pile of gypsum, and gypsum is calcium sulfate. So again, you've got a source of sulfur there, different microbes doing it, but either way you have this other source of hydrogen sulfide.
coming into the system. So then what you've got is you've got this nice hydrogen sulfide rich water migrating upward, taking advantage again of these enlarged fractures and faults, and you end up with super aggressive dissolution, which just means rock going away, right at the water table, because you get that oxygen mixed with hydrogen sulfide, you get sulfuric acid. There's a bunch of bugs involved in doing that process too, but you can look at it whether organically or inorganically. There's a lot going on right at that water table. You know, even before there were any entrances, this process was going on, but we're positive that once entrances like Carlsbad Cavern and stuff were actually formed, you then had so much oxygen able to go into the system that you could just self-perpetuate this whole process of generating the hydrogen sulfide, the sulfuric acid dissolve away cave, or dissolve away limestone and create cave. Just to give you kind of stepping back, this is the sky view of Carlsbad Cavern. I've got what mapped on here, breccia zones, and the breccia zones are just the faults where blocks of rock have fallen in and gotten kind of re-cemented together, but they're these big vertical zones of weakness that were pathways for the water. And then the Neptunian fissure, again, this is just a crack that's been filled with fairly fine-grained sediment, just indicating one of these areas where you had active faulting or fracturing going on all the way from Permian time to present. It was acted as that zone of weakness and as a source of contact between the meteoric water and hydrogen sulfide rich water. And then the rest of those blobs are just sort of kind of mapping out the geology. But the main thing is you can very clearly see the fracture orientation for Carlsbad Cavern. You know, you generally don't get those nice sharp right angles just at random. Those represent cracks in the rock that are the zone of weakness that facilitated the cave development. And then jumping over to the other big cave in the park, Lechuguilla Cave, very busy diagram. Again, the most important thing is those big red lines indicate actually mapped faults, and the U means that side was up, the D means that side was down. So that's all that fanciness means. The Guadalupe Ridge anticline, again, that's one of these A-shaped features that is a result of some of that faulting. And then the syncline is usually you have a bump up and then back down, and that down one is the syncline. Again, it's just looking at kind of the structural influence of these different things. And then this is the same kind of scheme as before, the breccia zones that are mapped, and then the Neptunian fissures. And then inside the cave, this is a view of Glacier Bay itself, which isn't that far inside the entrance of Lechuguilla Cave. In the kind of the cyan colored or light blue colored, you can see the sort of messed up jumble, whereas you see bedding to the left and bedding to the right, and you see that they're actually at different angles. So that's actually showing you that the left side of this has been lifted up, and the downside has been dropped down, and the little stick with the arrow on it, there's a person there for scale. About a 6-foot person. Yeah, I know there's a person because I took the picture. So you just have to trust me that there is a Stan Allison who is the person you can pose through the little cutout. That's also Stan. If you want to be Stan and be that person in the picture, you can go out and get your picture taken. Yeah.
I thought it was someone else.
No, that's definitely Stan. And then this is kind of a close-up. There's Stan again. This is in the Far East, looking at that fault, and you can see what he's standing right in front of. You see that just jumbled blocks with calcite cement all around, and then to the right you see the intact bedding. You can see the layers of the rock there. So that's what it looks like in the cave when you've got a nice clean view. So jumping back out to big picture, this is kind of a generalized schematic diagram of Lechuguilla Cave, and you see these very, very deep fracture zones. It's kind of the former inlet of the hydrogen sulfide rich water in a couple places, and then you can sort of see places where there's periods of development at very specific levels as the water table lowered. So now talking about that changing hydrology, the continued development of the Rio Grande Rift and the Salt Graben Basin. Again, you see the Guadalupe Mountains. That blue is the Capitan Formation itself. And you see now all the rock that was continuous up to the left has now dropped down, which what effectively starts cutting off your water supply. You no longer have this big mountain range feeding water into the deep aquifer. Your catchment area keeps getting smaller and smaller as those blocks get dropped down out of the way. And then this is it sort of schematically. About 29 million years ago was the onset of that rifting. And I've got the current water table, city of Carlsbad, shown way down on the bottom. But this is your big catchment area of the Capitan 29 million years ago. And then 11 million years ago, you see it's cut down. The upper parts, everything to the west of Guadalupe Peak has now dropped down. That's no longer supplying water into the system. And the water table is about at the level of Cottonwood Cave and Hell Below Cave, which are up in the National Forest. You see the area where we are right now is still well below the water table. So at that time, you're looking probably still at some enlargement of those big fractures, but not like the big cave development. And then about 4 to 7 million years ago, that's kind of the sweet spot for us. That's when the water table was basically at the level of Carlsbad Cavern and Lechuguilla Cave. That's when we started seeing all the big cave development. So you get the, initially you had like the development along the back cave level, and then some of the other horizontal levels, and kind of the last big stand for the water table was the big room itself, which is why it's so big. And then about 4 million years ago, the water table hit its current level. The active sulfuric acid cave development process is now cut off. There's still hydrogen sulfide being generated in the basin. There's still rain, albeit not a lot. We don't have the big catchment, so that process is no longer going on here in the park right where we are. There's still some potential that there's some cave development still going on where that mixing is happening, but that would still be like well below the water table and well away from us. And unfortunately, because of where the water table is, it's pretty much out of the Capitan limestone itself. So you're probably not looking at there's not like another big giant cave forming right now, and then our distant descendants will not have another cool Carlsbad Cavern located near the town of Carlsbad, because it's just not in that zone. So we get into the kind of the final phase of the cave development, which is kind of a lot of what attracts people to the cave. Is we've got breakdown collapse just as the water table drains, it loses the support for the roof. So that's when all those big blocks of rock that you see down in the cave came from, once it loses that support. And then right after that, you start getting the pretties forming. And that pretties is just this, is the simpler name for speleothem. And then another thing that we have happen is condensation corrosion. So we've got this warm, moist air down deep in the cave. And as that's moving up along the ceiling, it's actually causing corrosion of the bedrock itself, just because you're putting moisture against the wall and dissolving it. And then down below, where you've got the cold air coming down into the cave, those of you who went down, I'm sure noticed the very cool breeze constantly following you down into the cave. That's causing evaporation, so you end up with like popcorn growing down below that line. You end up with corrosion happening above that line. And in places like the lion's tail, you can actually see that very distinctly, where the top of the lion's tail is like very bare. You can see it's corroding, it's kind of chalky white. And then at the bottom, there's this big giant clump of popcorn, and that's the popcorn forming in the evaporation zone. So, those are the processes that are still going on now. Most of the massive formations, the giant, like Hollow Giants and Rock of Ages, all those big things of flowstone, all of the pools in the cave, those likely formed when it was a lot wetter down here, particularly during the glacial times when precipitation was much higher in this area. So, that stopped, somewhere in the 20 to 15,000 years ago is when those stopped growing as rapidly, and that was kind of the last time those pools were kind of actively filled. So now we're kind of in a drier time, and those pools still occasionally will fill up a little bit, but they don't stay full. So that's just part of the natural process of this whole area becoming more of a desert. But during wetter times, we definitely had a lot more water, and that's when all those big formations and the pretties that a lot of people want to see formed. And then that's it in a nutshell, or as much of a nutshell as I can accomplish without completely boring everybody.
The water table now is in the San Andreas formation, is that correct? I'm sorry, I'm like trying to.
It's not, it depends on where you are in the system, and it's the San Andreas.
Okay,
Yeah, that almost everyone pronounces it as San Andreas because they're used to the big fault in California.
yeah. How do you pronounce it?
San Andreas.
And dress.
Yeah, there's not a second A in there.
I have to come with diagrams, but I have questions.
No, but study aids are perfectly useful.
So could you talk a little bit about how we determine the ages of the different levels in the cave, and what's the process for dating that?
Yeah, absolutely. The main researcher that helped us kind of bracket those ages was Dr. Victor Polyak, who's currently at UNM on the verge of retiring, unfortunately. What he found was, and this was actually part of his PhD work, was, you know, in a lot of these pockets and stuff, you get clays that form, and some of the clays react to the sulfuric acid when they get to you know, a pH in that 1 to 3 range, you know, 1 being about the strength of battery acid. It will convert some of the clays to a mineral called alunite. And alunite is a potassium-rich clay, and you can actually do potassium dating, you know, back to around 50 million years. So knowing that you have to have this very low pH water contacting those clays sort of sets the clock of, at the very least, this zone was acidic at this particular time. You know, we know that the water table went up and down over time at various places, but it gives us a bracket on when these different levels were developed. And a lot of that work has then hence been corroborated by better understanding of the tectonics of the region, that it's actually matching up with some of these other events. Because like when he did his work, there was no one really looking at that whole, you know, Alvarado monocline type feature that controlled it, or really understood kind of what the catchment hydrology was. All that work has been done since then and independently, and hit about those same numbers where, yeah, they think that the water table was at this level at about the same time that Victor's work said that it was.
So how does Indolite help with that story?
Indolite doesn't.
Okay,
Indolite is one of the is also a byproduct of the whole speleogenesis process, but it does not have the right stuff in it to do dating.
okay.
Haliocyte is the rare clay that will then convert to alunite if it's exposed to super low pH.
Talk a lot about breccia, the importance of that as those larger rocks were falling, that's also creating faults. Because I was a little bit confused as to why you were correlating both the faults and the breccia on the same map, and I'm just trying to understand where the importance of that came in.
Yeah, the breccia formed during the faulting. It's just the expression that we see, because you're opening up a crack that the rocks can fall
Got it.
into.
Which is similar to that line that you had on the Carlsbad one that filled with sand instead of rocks that filled with sand, and that's
Correct.
Got it.
Correct. And deeper down in the system, those cracks were barely open at all, but they still provided fluid flow. And those of you who spend a lot of time in the backcountry around here, you know that like as you're going up the canyon, there's all these fins that come out. Those are also expressions of that syndepositional faulting. But the early fluids basically dolomitized the area right around those fractures down deep. And the dolomite is much more resistant to erosion and dissolution than regular limestone. So that's why they're resistant. That's why they stick out. If you've read a lot of the early research, people were noticed, like even in the 60s, that there seemed to be a correlation between cave entrances and those big fins, but they just couldn't kind of make the connect of why that was the case. Leslie Malem, when she was working with Peter Scholl up at University of Wisconsin, was the first to kind of document that dolomitization of those fractures, but didn't sort of carry it to the next step of what does that mean. It wasn't really until Edward Hunt and COSA started doing their work in Slaughter Canyon and actually started mapping the stratigraphy and seeing that there were clearly faults that formed during the Permian. And way up in the back reef, they expressed themselves as little anticlines and synclines, but as they followed them deeper, they would actually see the actual displaced rock, they'd see the breccia zones, and you keep tracing them down and they end up with just these highly dolomitized zones. So they were the ones who kind of put together that whole tectonic story, and that wasn't until the mid-90s that they came up with that and started doing the detailed work that actually showed that these faults were actually growing during Permian time.
So in the entrance, there's a teepee structure. I'm still a little confused, because on the way up, you can see them on Walnut Canyon, how, I know it's something to relate with water coming through, but I'm still a little confused.
Sort of yes, sort of no.
Okay,
Think of the teepee structures as big mud cracks.
okay,
They generally only form in on carbonate platforms where it's extremely arid. Like the only place that we see them now is like in areas around Saudi Arabia on those big Sabga plains. So they're polygonal features. So no matter what section you draw through the rock, you're going to see the teepee structure. So they're not long and linear. They actually are polygons, just like a mud crack would be. And what happened is water did come up through those, and that's what kind of forced them to stay open. They didn't just, when they got wet again, they just didn't go right back. Because you still have water moving through, it helps cement those things open, and it'll let them be persistent in the same place going all the way up through the stratigraphy. So you can see like teepee structures that are 10, 15 meters tall, but an individual mud crack was not gonna be that big. So it just kept those things open, and somewhat of the cool thing about those teepee structures, those polygonal features, is sediments would roll around inside of the little bowls, and that's where you get the concentration of the pisolites. And that's just from water moving as the stuff got cemented together, and so you frequently end up with basically bowls of pisolites inside the teepee structures. And the teepee structures themselves are also a little area of weakness, so you don't notice it very much in any cave except for Spider. That a lot of the weird maziness of Spider is not due to a lot of those big fractures. There's fracture control there too, but those rooms that have very distinct ways out of, and then go to another room that has the same kind of thing, they're actually getting dissolution along the teepee structures. You're kind of re-excavating those bowls.
I always thought it was cool because along Walnut Canyon where that big hairpin turns, you can see that huge one.
Right.
And then you go in the entrance and there's this cute little.
Yeah, and there's some really nice ones at the edge of the parking lot over here too. That's a lot of geology groups go over there and look at that. Any other questions? Either I answered them all, or you decided that was going to be way too nerdy of an answer and don't want to ask another
I
question.
think I have a question.
Sure.
So you mentioned the, so there's sawtooth structure? Not blanking, but with was that what you were saying was linked to the syndepositional faulting?
Are you talking about dogtooth?
Dogtooth, sorry.
Yeah, those were sort of related just because you still have to have that fluid flow connection, but those pockets of the big calcite spar are not related to modern cave development at all. They're features that the modern cave has cut through, but those showed very little influence on later cave development. So they're individual features that we see. The most impressive is the area called Spar City in the western branch of Lechuguilla Cave, where there's a whole bunch of passage down there that it's lined with nothing but that giant spar. In fact, that's where that picture that Dave was taken next to, that's down in Spar City. So you do intersect these old pockets, but they're not what you would consider the modern cave. So we get little rooms that are made from those pockets, but it didn't the rest of the cave didn't develop around those pockets. But it still had to have that
those fractures and stuff to get the water movement, so you get the CO2 in there and form the pockets initially, and then with pressure and temperature changes, form the crystals again right after.
I remembered it spaced out, but the fins was the word I was thinking of.
Oh, fins.
Yeah, sorry.
Yeah, the fins are related to those syndepositional faults and fractures. Basically, they're linear features. If they've got movement on them, then they're considered a fault. If there's no appreciable movement, it's just a fracture.
And now, where are those visible at?
In almost every canyon in the Guadalupe.
Oh, okay, so that's, okay, I know what you're talking about, you can see them driving around.
Yeah, I mean, obviously out on the flats, you're not gonna see them, but in the mountains, you go up Slaughter Canyon, and you know, like the elephant, that's one of those big fins.
Yeah, thanks.
Yeah, no problem.
I'm sorry to keep clarifying. When you said the entrances are typically following, for a lot of these caves are typically following where those faults are, those pre-existing weakening points, and that's what's eventually creating the entrances to a lot of these caves. I'm not a geologist. I'm doing the best I can with limited knowledge here.
No, we don't necessarily see, the fault breccias and everything in all of the entrances, like, there's nothing to indicate, like, Carlsbad itself was on a fault, like the Carlsbad entrance. Lechuguilla entrance, absolutely, you can see the breccia right there, you can follow that fault all the way to, Glacier Bay, but you still have these fractures. So like I said, you had these zones of weakness that were still caused because of that early Permian activity. Not all of them had enough movement that you would see it as a fault. We can't really map the stratigraphy very well across like the main corridor to see that there's any kind of displacement. I don't see any evidence of a fault there. There's definitely like one of those Neptunian dikes and some breccia like way out in the Guadalupe room. Which is obviously not on the main trail, but you do see it in the Guadalupe room and in a couple other places where it's actually exposed. New Mexico room is another one where you actually see the Neptunian dikes. You don't see the breccia, but you see the Neptunian dikes.
So what you're saying is that there may not have been a full fault or fracture, like a true crack in the rock, but there might have been an area of weakness, and that pre-existing weakness is what helped lead to the entrance of some of the caves that we're seeing here. Some of them are also sometimes falling on faults. Am I understanding correctly? Got it.
Yeah. To form the cave, you had to have some sort of crack for some sort of discontinuity for water movement. And that would include the Carlsbad entrance, which may have just been a pretty significant crack, but not necessarily one that had movement on it. Because clearly it's a very straight line from the entrance all the way down to, the scenic rooms.
I have another question, but it might be too nerdy.
It's not gonna be too nerdy for me.
So I think it's in the papoose room, there's spar that has, I think, either secondary or tertiary deposition of calcite, and they almost are round. And it's like, it's like past, you know what I'm talking about? Is that, was that area like intersect, so the spar formed first, that void was there first, and then the cave intersected it again, and that new, I guess, epigenetic water deposited the calcite, or what do you think happened?
Yeah, I mean, that's exactly what it is. You're basically, you're getting mammillaries, the underwater deposits forming on top of the spar.
Okay, yeah, I don't know if it was so I had no idea.
I'm pretty sure in the Papoose area, I think that's still subaqueous mammillary development, just like it.
Yeah,
like
but
the
it's
clouds.
cool because you can tell it's actually on top of the sky.
Yep. That wasn't too nerdy.
Okay.
Where in the papoose room is that?
I could walk there. I don't think. It's where like those weird, interesting near where the antler formations at the back are off trail.
Okay.
Like you have all those really cool antler formations.
Like
and then
if you follow the flagging visually, would you kind of get a little bit closer to where you can kind of find? Don't worry about it. I'll figure it out.
Yeah.
That's too nerdy for you.
And then there's like a pool, and then there's calcite.
Corner Devra next to a map and make a point.
I can, if you give me a map, I can show you where it is.
That's gonna take me a while. I still don't know how to access
I'll
our
find a
GSX
picture.
maps.
Yeah,
I'll find a picture of the room.
yeah, I mean, like, that I can do, and I can walk there, but like, how else do you, yeah,
That's why we made nets.
yeah.
All right, well, if there's no other questions, thank you all for coming, I appreciate it. And have a great rest of your stay at Carlsbad Cavern. Hopefully you get some good tours in and enjoy this awesome weather and lots of sunlight and daylight. Fairly soon I'm going back to where it's dark all the time.
It's